Guys, welcome to our first ever lecture. Today we're going to be talking about calculus and in specific functions. This is 1.1 functions. So let's get right into it. Should be a lot of review for many of you, but we're going to take our time and assume nothing. So let's go ahead. So a function looks like this. Y equals f of x is how it's read. And it just basically means that for every input, or x, we have, this function churns that input and creates an output y. D is the domain, which is all x's that can be input into this function here. So assuming we can continue, y equals pi r squared. This is a function, and we just replaced x with r in this example, but we could easily have any letter here. We just use r because it is the commonly noted radius of a circle. So if we're using pi r squared, which is the formula for the area of a circle, then we can look at a couple of inputs, or r's, that belong in the domain, and then look at what our outputs, or y's, are going to be. So over here on the right hand side of the screen, over here, we have r equals 0, would give us an output of 0, because we can just plug that into the function. And then we can input r equals 1 equals y equals 1, r equals 2, so 2 squared. Oh, I forgot my pi here. Whoopsies. So let's make sure we get those because those are important, right? So we got our pi in. So then r equals 2, 2 squared is 4, and y equals 4 pi, because pi is a constant, remember? So let's look at a couple of different functions. We have the function y equals x squared, which has a domain of negative infinity to infinity. Basically, you can plug in any number and it will give you an output. Good thing to note here is that we have the curly brackets here, which basically denotes that it approaches these limits, which we'll get into later. But the idea is that you can never reach infinity. It just stretches all numbers. So then our outputs, or our range of outputs, that means all y's that we can produce, are going to be hard bracket here, 0 to infinity. We use the hard bracket here because this is a definite limit. You can't have a negative x, or you can't have a negative squared number. We'll move into our next function, y equals the square root of x. Now this is a little bit more complicated. Basically the idea here is that it's hard bracket 0 comma infinity soft bracket, and so with this hard bracket you can't take the square root of a negative number without getting into imaginary numbers, so we assume the limit to be 0, and that is exactly what the range is, as well as you can see evidenced here. So 0 comma infinity. Finally, we'll move into our last example function, y equals 1 over x, or x to the negative 1 power. This is a union symbol here, the thing that looks like a U, so we'll get right into that. The domain is negative infinity to 0. We have a curly bracket here, so you see that you can't have 0 because you can't divide by 0, correct? Union with 0, because now we have our limit again on the upside of this, going to infinity. So we can have every number in the spectrum except for 0, because we can't divide by 0. And it produces the exact same range. And you can see that if you were to start plugging in numbers, you would get this exact range. So now we're going to look at a quick example, or a quick example. And here we have our x squared function, but I just graphed it for a few points on the positive side of things, just to make it simple for you. It also has another offshoot that comes up on this side, right? But if we're just taking a look at this right side here, you have to identify how something is a function, right? And one of the easiest ways to do that, graphically speaking, is the vertical line test. And so what this means basically is the idea that we draw lines that run vertically all the way down. And I should use a different color, but they run all the way down, right? And we can draw as many of these lines as possible, and for each x in our domain there is a unique y output. So basically, if you had a vertical line and you had a function that looped back on itself, or had multiple outputs for a single input, then it's not a function anymore, okay? So let's hop into our next topic, symmetry. Once again, symmetry here is so we can either have odd functions or even functions. And so even functions are if y, or f of negative x equals f of x. then that would be an even function, and I'll explain that in a minute. Odd functions, if f of negative x equals negative f of x, and that is for every x in D, which is our domain, remember? So a quick example of what an even function looks like is x squared. As you can see, it matches perfectly across the y-axis as well, which is kind of nifty, but anyways, it's even because if we were to say, if this was our negative 1 and this was our 1, right, if we're just to put those numbers in real quick, negative 1 squared is going to be 1 squared, which is 1. So if we were to input a negative x, we would get the same output as if we just use a regular x. And then so if we're going to take a look at an odd function, like x cubed over here, then f of negative x is equal to negative f of x. So here if we put in f of 1 equals 1, if you're just doing a quick mental math, but if you were to put in negative 1, f of negative 1 would be negative 1. And so what this perpetrates is the idea that here's our negative 1 and here's our 1, and so it's equal to 1 up here, but it's equal to negative 1 down here. And what that means is that it's just symmetric about the origin instead of the y-axis like our even functions. And finally, we're going to head into different types of functions, common types of functions. So the first one of those is linear. These are usually in the general form f of x equals mx plus b, with m and b both being constants. For an example function, and a very important one, is the identity function. This is f of x equals x. So this is an m equals 1, b equals 0, and that's this green line over here on the right that you can see right over here. And so this stretches into infinity and basically passes through the origin, and every point here x equals y. Next we have power functions. This is f of x equals x2 and a. That's an a, by the way. And here we have a lot of different functions going on. I know I drew them in quick succession, but I wanted to give you a comparison so that way you could see them. So first of all, we're going to start with f of x squared, which is this the red one on here. And so what this is you can see that it touches the touches the x-axis at 0, and quickly moves away from the x-axis after x equals 1 or negative 1. Next we have this yellow function, which is x cubed, and so you can see that it spends a little bit more time between 0 and 1 respectively, nearer to the origin, and that's because it's less than, if x is less than 1, then it's going to tend to stay towards the or to the x-axis the higher power we get. So this yellow is x cubed, and then finally this green one here is x to the 4th. And you can see that once again it's a bit wider and closer to the x-axis than our x squared function. And then finally we have x to the 5th, which is this light blue function here, and it spends even more time than our previous functions. And you could see that if we were to continue this trend, we would have a function that stays very close to the x-axis within 0 to 1 and 0 to negative 1. Next we have functions of a power less than 1, and so for example we have the function this pink one right here that only comes off this one way, is the x to the 1/2, so that would be something like this, or it also is the square root function. And so you can see that our domain, remember that it's a positive domain and a positive range, so you can see that it never dips below the x-axis and it never dips behind the y-axis if we're looking at it like that. And next we have the x to the 1/3, and you can see that this is a odd function like its respective partner x cubed, and so you can see that it is symmetric about the origin and also has a positive and negative value. Next we have rational functions, and we're going to get into these a little bit later, but it's basically that f of x equals p of x over q of x, and these are both polynomial functions. Next we're going to move into trig functions, and once again we're going to cover a lot of this later, but f of x equals sine of x. This is a periodic function, meaning that it repeats after a given period. Here it's 2 pi, so if we were to look at 0 here, and then the next time, so it comes up and goes down, and then it repeats that right here. So this is 2 pi right here where I made that blue arrow, and then you can see that it repeats it again right here at 4 pi, and if we were to continue the other direction, it would repeat every 2 pi as well. And then the cosine function right here is also periodic. I prefer to use points on the x-axis that are equal to 0. So if we were to look at pi, for example, which would be where it crosses the x-axis right here, and then the next time that it repeats this idea, it is once again 2 pi periodic function. Hey guys, so let's finish out this episode with one last slide. So here we have piecewise functions. This is something like a function that is formed of broken down into 2 smaller parts and then formed of 2 functions. So to graphically represent absolute value of x, we could write it like this. X, it's equal to x if x is greater than or equal to 0, but it's equal to negative x if x is less than 0. So if we were to do this, so you could see like here, if we say this is 1 and this is negative 1, so since 1 is greater than or equal to 0, it's equal to x, so absolute value of 1 is 1, and then if it's less than 0, like negative 1, the negative of negative 1 is 1, so the absolute value of negative 1 is 1, and you can see that graphically represented here. Next, we are going to move on to greatest integer and least integer functions. So these are also known as floor and ceiling functions. Our floor function here basically drops any integer down to the number below it. So as you can see, if we take a look at a couple examples, if we input 2.4 into the greatest integer function, we get 2. If we input 1.9 into the greatest integer function, then we get 1. If we input negative 0.3 into the greatest integer function, then we get negative 1. And you can see it's graphically represented here on the right. I did have to enlarge those circles a little bit, but basically what it's saying is that these circles represent holes that are filled by the piece above it. So here is negative 1 and negative 1, and all these numbers approaching 0 all are negative 1, but as soon as you get to 0, that gets bumped up to the next one. So at 0, and then from all the numbers between 0 and 1 are equal to 0. And then at 1, the same thing happens. At 1, and all the numbers up to 2, but not 2 itself, are equal to 1, and so that trend just continues upwards and downwards. Next, we have least integer functions. You can see this is the ceiling function. So 2.4 becomes 3, negative 2.2 becomes 0, pi becomes 4, and I didn't graphically represent that, but it's basically if you have the y equals x curve, it's just on the flip side of that, so kind of like that, although that was an awful circle that looked more like a heart. Last but not least, we have the exponential and logarithmic functions. For exponential, we have f of x is equal to some constant a to the x power. I drew that's this first one here. We have, in this bright lime green, we have 2 to the x, and you can see that it increases at a much slower rate than our other examples here. So this middle one, that's kind of an army green, could be our 5 to y, or f of x equals 5 to the x. You can see that it increases a bit faster than 2 to the x. And then finally we could have f of x equals 10 to the x, which is this top function here that kind of turns upwards right at the end, and so that would be the greater the base number, the faster it is going to increase, and that is due to common sense, really. Logarithmic functions, f of x equals log base a of x, and just a little tidbit on your calculator, base a is almost always going to be equal to 10. So in this we have, that's the example all the way on the right there, and so here the one closest to our x-axis and the lightest is log base 10 of x, and you can see that stays a little bit closer to our axes along the y here down in the fourth quadrant, and in the first quadrant it is closer to our x-axis, and then you can see these start to push further away as we decrease our base number. So if we have base 5, that's that one in the middle there, that's kind of that aqua, and then finally this darker blue that I'm running along here is a log base 2. So thank you for joining me, guys. I hope you really enjoyed, and don't forget to check out next episode. Thanks.